Apple just published a research paper talking about how everything we knew about LLM reasoning and thinking is wrong. After the paper was published, I saw two main trends. On one side, people are saying that Apple is just doing this to stay relevant since they couldn't crack AI and that whatever they said is wrong. And on the other side, I see people saying that they knew all along that LLM didn't have reasoning or thinking capabilities and that they didn't need a new research paper to say that. And the truth is, regardless of where you stand in that conflict, research paper does contain a lot of interesting stuff and a lot of nice topics to talk about. Let's dive deep into what the paper said, see what kind of tests they did, the results of those tests, and then we can understand where they're coming from and see if we also agree if what they said is true or not. Let's jump right in. The Illusion of Thinking is a paper published by Apple very recently aimed at comparing large reasoning models with their large language model counterparts. While everyone here knows that large language models are models that are created to do smooth text, large reasoning models are a way of taking these models and retraining them so that they're used for reasoning. Basically, the data sets are made of reasoning tasks that made sure that the models learn to do step by step complex problem solving, as well as a focus on using more reasoning and thinking. These models also perform a thinking step where they generate their, let's say, thinking outputs to make sure that they show their chain of thoughts. The researchers in the paper wanted to compare the effects of adding or removing these reasoning capabilities on complex puzzle programs. The idea was to compare these models on similar inference compute. They show the results on three different regimes: low complexity tasks, medium complexity tasks, and high complexity tasks. They created these puzzle environments where they were able to change the complexity of the problem by changing smaller parameters. What they were able to show is that low complexity tasks give an edge to normal language models, while medium complexity tasks have an advantage for reasoner models, and at high complexity tasks, both models actually collapse and perform very poorly. The paper actually started by explaining that normal benchmarks have a lot of inconsistencies, meaning that for different math benchmarking, for example, you would see that reasoning models sometimes do better, while normal language models would sometimes do better. And this inconsistency led them to think whether or not reasoning models are actually enhancing the capabilities by what we think by adding the model to reason more or to think better. So they wanted to be able to test the models on puzzle environments, specifically designed so that they're able to change the complexity where the way of solving the puzzles, the logical reasoning doesn't change. It just becomes way more complex as the number of steps that they have to do goes up. They said that by maintaining complex logical processes, they are able to do a more precise analysis of these thinking tokens and see how the model actually performs. In the research, they focus on four different puzzle environments: the Tower of Hanoi, checkers jumping, river crossing, and blocks world. So how did the testing work? They focused on models that are able to generate the thinking tokens and that they have access to. The idea is that they can use these thinking tokens or text generated within them for analysis, and then they can also have an idea on what goes inside the mind of the model as it's trying to solve the problem. The way the analysis works is that the model generates its thinking output as well as its final solution. And then the final solution is analyzed for precision. So this is where they see if the model solution actually is a successful one. And then they also look to analyze the thinking output to see when the correct solution was found, how the model reacted to finding a wrong solution, and just to overall see the analysis of the model reasoning. So what results did they observe? Further testing, they tested this on DeepSeek as well as Claude, and they realized very similar patterns when it comes to both models. For low complexity tasks, both the reasoning and normal models do very well, but as the complexity goes up, their performance starts to decrease until it reaches a certain point where the high complexity starts and both models collapse entirely to zero precision. They also wanted to monitor how long in the reasoning output does the model take in order to find the correct solution. So they would check in the model reasoning when the first iteration of the correct solution was found. And what they realize is that when the final answer is correct, the model actually finds the correct solution in its reasoning very early on. While when the output at the end is wrong, what happens is that the model usually fixates on a wrong answer very early on and keeps wasting its remaining pockets trying to make it work. They also wanted to compare the pass-at-k performance metric. The pass-at-k performance metric is a way for us to check multiple solutions and get the probability of finding at least one of them to be a correct solution. So if we give the same problems to the LLM n times, pass-at-k would be the probability of finding a correct solution in at least one of them. So a higher probability means that the model is better at generating a solutions, that we're more confident that we're going to find the correct solution in them. So for example, if a model is really good and given n problems, they will answer every single one correctly, the probability will be at 100%, meaning that we are very sure to always find at least one. But if all of them are correct, then that's also trivial, right? What they realized here is that for low complexity tasks, normal LLM models actually perform better than the reasoning ones. And it's not until the complexity is up until medium complexity where the reasoning model starts having an edge, while then at the end, at some critical point, both models just drop completely to zero, meaning that they never generate the correct answer anymore. They also wanted to monitor the token lengths in thinking models. So, for example, how long is the output in their, let's say, reasoning compared to how complex the problem is. The idea here is that for complex problems, you would need to think more, and then the token lengths will be higher. What they noticed is that for low complexity problems, the reasoning tokens are, let's say, short sized. And as they ramped up the complexity for medium complexity, the size did increase. However, there was a point where afterwards, as they were heading up in higher complexities towards high complexity, the number of tokens actually decreased, meaning that the model was reasoning less. This, of course, is way opposite to what we would expect to happen, as we would expect for the token number to keep increasing as the complexity of the problem kept increasing. The next test they did was that they wanted to check the algorithmic capability of a model by giving the algorithmic solution to the model and asking it to use it to find the solution. The idea here, if I gave you the step-by-step guide on how to fix any of these problems, you would be able to trace that algorithm to be able to find the solution at the end. What they noticed is that even given the algorithm to solve the problem, the models were not able to still capture any of the solution in the high complexity problems. At the end of the paper, the researchers also noted that while these environments are really good at allowing them to change the complexity of the problem, they are a very narrow slice in the domain of problem solving, that they do not really capture every single problem solving in the real world, and that someone would need to expand on these to test the models within, let's say, more complex problems. They also stated that all of their experiments relied on black box API calls, meaning that they only had access to changing the inputs and receiving the output. What they meant was is that they couldn't really test the internal working of the models. They wanted to check if they can change the input or output and then test the neuron activation and see if that entails how the model really works internally, depending on how the complex the problem is. But because they were only using the API, they couldn't really do that. So, what do we learn from all of this? Despite your stance on AI's capabilities of creating their own LLM or their own AI model, it doesn't take away from how comprehensive and quite good the evaluations in this paper is. See, reasoning models are wildly thought of as these very smart machines that are able to do their own reasoning and are even being sold to people as, this is the next step before AGI. And having a way for us to evaluate these models and benchmark them on, let's say, tasks that they weren't specifically trained for is a good way for us to monitor how smart these models are and how we should actually look at them. See, reasoning models, while are smarter and perform better in some cases, there is still the notion of them being able to generate their own thoughts, right? But these thoughts are in a way similar to how a normal LLM processes output. It's still kind of generated based on the best pattern that they can match. And this is all based on their training data set. It doesn't mean that they form their own reasoning and that they think about it, rather than that they still just perform some sense of autocomplete. The reason that they perform better than normal LLMs on some stuff is twofold. It's two main things. On one hand, they are trained on data that specifically forces them to do, let's say, more thinking, more reasoning, but also because now you have these thinking tokens and now you have these inputs that go before the solution. This gives the model more context. This gives the model more idea on plans on how to solve the problem, but also more context on the problem, which, as we all know, more context for LLMs is usually a factor in them performing better. I see a lot of people arguing that we cannot call LLMs as non-reasoning machines or non-thinking machines because humans also fall short in similar situations. So, for example, what they're saying is that because humans also have the same problems when solving very complex problems, we cannot call machines as non-thinking machines, which, while fair, is quite biased. We seem to hype up every single paper, every single thing that anyone says about LLMs performing good on a certain problem, while the minute someone says this is where LLMs fall short, this is where AI does something wrong, we seem to give excuses. We seem to say, oh, but this is exactly like humans. So either we're all for that AI is way better than humans and they should not be doing the same mistakes that humans do, or we agree that AI does mistakes and they do exactly the same as humans do, so that if a human does something wrong, AI can do it wrong too. But then we are not really getting this great AI that is very smart and does everything correct. We have on one side companies that have their entire sponsoring, their entire funding, and their entire livelihood focused on the fact that they sell AI models and that they need the entire world to believe that they're giving us the AGI within the next 3 years or less, and that they're always going to be performing better models and that AI models are the smartest things they can ever sell. And then we have some researchers and smaller companies that are talking about how AI in this step is not there yet and that we're way farther than people are making you believe, but no one really believes them. The truth is, and what I still believe reading this paper or testing LLMs myself, is that while they are smart and while they do have situations where they shine very bright, they are still just predictive engines that mimic their training data. They basically are really good at doing text completion at a very large scale. And if we expect AGI to be nothing more than an LLM that can just do autocomplete on a larger scale, then maybe we don't really understand AGI as we think we do. The truth is, anyone who's ever used LLMs in a, let's say, complex or specific problem knows how frustrating it is to get LLMs to do the right thing. When it comes to easy problems that exist more often or are very repetitive, LLMs are doing great at solving these things. So LLMs is a really good tool to automate repetitive tasks that are easy and are, let's say, happening more often. But when it comes to problems that are very specific to a very narrow domain, LLMs are very bad at solving these problems. And this is something that we get with overgeneralization, because once you know everything, there's very small details get lost. But it's also something that happens when most of these specific problem are behind some NDAs, where, for example, code for large companies that is focusing on all the good things you should do is often hidden in a way where OpenAI or whatever other company can train on it. And if the model only sees what's publicly available on the internet, it's usually seeing a lot of bad generated outputs as well as good ones, but also AI generated outputs. So it's also training on its own outputs, which have hallucinations. And that causes LLMs to be really bad at specific problems. Now, whether or not these problems mean that it's bad, no, it doesn't. LLMs are good and they are a great tool, but they aren't as close to whatever smart being artificial superintelligence is, or even artificial general intelligence. They are generally intelligent in the sense that they know general knowledge of everything because they're trained on everything. But they are just pattern matching and not necessarily reasoning about their outputs. However, whether you believe that or whether you believe Apple is correct about their paper or not is up to you to decide. This will be all the talking I do in this episode. I hope that this gave you an understanding of how the paper works and what they meant by their testing, and maybe also gave you an idea on whether or not to trust LLMs and their reasoning capability. Let me know what you think about all of this in the comments below. Thanks for listening, and I'll see you in the next episode.